Static routing. The show IP route command is used to display the routing table. Initially, the routing table is empty if no interfaces have been configured. As you can see in the routing table for R1, no interfaces have been configured with an IP address and subnet mask. Note: static routes and dynamic routes will not be added to the routing table until the appropriate local interfaces, also known as the exit interfaces, have been configured on the router. Interfaces and their status. The status of each interface can be examined by using several commands. The Show Interfaces command shows the status and gives a detailed description for all interfaces on the router. As you can see, the output from the command can be rather lengthy. To view the same information, but for a specific interface, such as Fast Ethernet 0/0, use the Show Interfaces command with a parameter that specifies the interface. Notice that the interface is administratively down and the line protocol is down. Administratively down means that the interface is currently in the shutdown mode, or turned off. Line protocol is down means, in this case, that the interface is not receiving a carrier signal from a switch or the hub. This condition may also be due to the fact that the interface is in shutdown mode. You will notice that the Show Interfaces command does not show any IP addresses on R1's interfaces. The reason for this is because we have not yet configured IP addresses on any of the interfaces. Additional commands for examining interface status. The Show IP Interface Brief command can be used to see a portion of the interface information in a condensed format. The Show Running Config command displays the current configuration file that the router is using. Configuration commands are temporarily stored in the running configuration file and implemented immediately by the router. Using this command is another way to verify the status of an interface such as Fast Ethernet 0/0. However, using Show Running Config is not necessarily the best way to verify interface configurations. Use the Show IP Interface Brief command to quickly verify that interfaces are up, and administratively up, and line protocol is up. As shown, R1 does not yet have any routes. Let's add a route by configuring an interface and explore exactly what happens when that interface is activated. By default, all router interfaces are shut down, or turned off. To enable this interface, use the No Shutdown command, which changes the interface from administratively down to up. Both of these messages are important. The first change state to up message indicates that, physically, the connection is good. If you do not get this first message, be sure that the interface is properly connected to a switch or a hub. Note: although enabled with no shutdown, an Ethernet interface will not be active, or up, unless it is receiving a carrier signal from another device switch, hub, PC, or another router. The second change state to up message indicates that the data link layer is operational. On LAN interfaces, we do not normally change the data link layer parameters. However, WAN interfaces in a lab environment require clocking on one side of the link. If you do not correctly set the clock rate, then line protocol the data link layer will not change to up. Unsolicited messages from iOS. The iOS often sends unsolicited messages similar to the change state to up messages just discussed. As you can see in the figure, sometimes these messages will occur when you are in the middle of typing a command, such as configuring a description for the interface. The iOS message does not affect the command, but it can cause you to lose your place when typing. In order to keep the unsolicited output separate from your input, enter line configuration mode for the console port and add a logging synchronous command, as shown. you will see that messages returned by iOS no longer interfere with your typing. Reading the routing table. Now look at routing table shown in the figure. Notice R1 now has a directly connected fast Ethernet 00th interface, a new network. The interface was configured with the 172.16.3.1/24 IP address, which makes it a member of the 172.16.3.0/24 network. The C at the beginning of the root indicates that this is a directly connected network. In other words, R1 has an interface that belongs to this network. The meaning of C is defined in the list of codes at the top of the routing table. The /24 subnet mask for this root is displayed in the line above the actual root. Routers usually store network addresses. With very few exceptions, routing tables have roots for network addresses rather than individual host addresses. The 172.16.3.0/24 root in the routing table means that this root matches all packets with a destination address belonging to this network. Having a single root represent an entire network of host IP addresses makes the routing table smaller, with fewer roots, which results in faster routing table lookups. The routing table could contain all 254 individual host IP addresses for the 172.16.3.0/24 network, but that is an inefficient way of storing addresses. A phone book is a good analogy for a routing table structure. A phone book is a list of names and phone numbers, sorted in alphabetical order by last name. When looking for a number, we can assume that the fewer names there are in the book, the faster it will be to find a particular name. A phone book of 20 pages and perhaps 2,000 entries will be much easier to search than a book of 200 pages and 20,000 entries. The phone book only contains one listing for each phone number. For example, the Stanford family might be listed as Stanford, Harold, 742 Evergreen Terrace, 555-1234. This is a single entry for everyone who lives at this address and has the same phone number. The phone book could contain a listing for every individual, but this would increase the size of the phone book. For example, there could be a separate listing for Harold Stanford, Margaret Stanford, Brad Stanford, Leslie Stanford, and Maggie Stanford, all with the same address and phone number. If this were done for every family, the phone book would be larger and take longer to search. The show interface's fast Ethernet 00th command in the figure now shows that the interface is up, and the line protocol is up. The no shutdown command changed the interface from administratively down to up. Notice that the IP address is now displayed. The show IP interface brief command also verifies this same information. Under the status and protocol, you should see up. The show running config command shows the current configuration of this interface. When the interface is disabled, the running config command displays shutdown. However, when the interface is enabled, no shutdown is not displayed. A router cannot have multiple interfaces that belong to the same IP subnet. Each interface must belong to a separate subnet. For example, a router cannot have both its fast Ethernet 00th interface configured as 172.16.3.1/24 address and mask and its fast Ethernet 01st interface configured as 172.16.3.2/24. The iOS will return an error message if you attempt to configure the second interface with the same IP subnet as the first interface. Typically, the router's Ethernet or fast Ethernet interface will be the default gateway IP address for any devices on that LAN. For example, PC1 would be configured with a host IP address belonging to the 172.16.3.0/24 network, with a default gateway IP address 172.16.3.1. 172.16.3.1 is router R1's fast Ethernet IP address. Remember, a router's Ethernet or fast Ethernet interface will also participate in the ARP process as a member of that Ethernet network. Ethernet interfaces participate in ARP. A router's Ethernet interface participates in a LAN network just like any other device on that network. This means that these interfaces have a layer 2 MAC address, as shown in the figure. The Show Interfaces command displays the MAC address for the Ethernet interfaces. As demonstrated in Chapter 1, an Ethernet interface participates in ARP requests and replies and maintains an ARP table. If a router has a packet destined for a device on a directly connected Ethernet network, it checks the ARP table for an entry with that destination IP address in order to map it to the MAC address. If the ARP table does not contain this IP address, the Ethernet interface sends out an ARP request. The device with the destination IP address sends back an ARP reply that lists its MAC address. The IP address and MAC address information is then added to the ARP table for that Ethernet interface. The router is now able to encapsulate the IP packet into an Ethernet frame with the destination MAC address from its ARP table. The Ethernet frame, with the encapsulated packet, is then sent via that Ethernet interface. Next, let's configure the serial 0/0/0 interface on router R1. This interface is on the 172.16.2.0/24 network and is assigned the IP address and subnet mask of 172.16.2.1/24. The process we use for the configuration of the serial interface 0/0/0 is similar to the process we used to configure the fast Ethernet 00th interface. After entering the commands above, the state of the serial interface may vary depending upon the type of WAN connection. This will be discussed in more detail in a later course. In this course, we will be using dedicated, serial point-to-point connections between two routers. The serial interface will be in the up state only after the other end of the serial link has also been properly configured. We can display the current state of serial 0/0/0 using the Show Interfaces serial 0/0/0 command, as shown in the figure. As you can see, the link is still down. The link is down because we have not yet configured and enabled the other end of the serial link. We will now configure the other end of this link, serial 0/0/0 link for router R2. Note, there is no requirement that both ends of the serial link use the same interface, in this case, serial 0/0/0. However, because both interfaces are members of the same network, they both must have IP addresses that belong to the 172.16.2.0/24 network. The terms network and subnet can be used interchangeably in this case. R2's interface serial 0/0/0 is configured with the IP address and subnet mask 172.16.2.2/24. If we now issue the Show Interfaces serial 0/0/0 command on either router, we still see that the link is up-down. The physical link between R1 and R2 is up because both ends of the serial link have been configured correctly with an IP address mask and enabled with the No Shutdown command. However, the line protocol is still down. This is because the interface is not receiving a clock signal. There is still one more command that we need to enter, the clock rate command, on the router with the DCE cable. The clock rate command will set the clock signal for the link. The WAN physical layer describes the interface between the data terminal equipment DTE and the data circuit terminating equipment DCE. Generally, the DCE is the service provider and the DTE is the attached device. In this model, the services offered to the DTE are made available either through a modem or a CSUDSU. Typically, the router is the DTE device and is connected to a CSUDSU, which is the DCE device. The CSUDSU DCE device is used to convert the data from the router DTE device into a form acceptable to the WAN service provider. The CSUDSU DCE device is also responsible for converting the data from the WAN service provider into a form acceptable by the router DTE device. The router is usually connected to the CSUDSU using a serial DTE cable, as shown. Serial interfaces require a clock signal to control the timing of the communications. In most environments, the service provider, a DCE device such as a CSUDSU, will provide the clock. By default, Cisco routers are DTE devices. However, in a lab environment, we are not using any CSUDSUs and, of course, we do not have a WAN service provider. For serial links that are directly interconnected, as in a lab environment, one side of a connection must be considered a DCE and provide a clocking signal. Although Cisco serial interfaces are DTE devices by default, they can be configured as DCE devices. To configure a router to be the DCE device: 1. Connect the DCE end of the cable to the serial interface. 2. Configure the clock signal on the serial interface using the clock rate command. The serial cables used in the lab are typically one of two types. A DTE-DCE crossover cable on which one end is DTE and the other end is DCE. A DTE cable connected to a DCE cable. In our lab topology, the serial 0/0/0 interface on R1 is connected with the DCE end of the cable, and the serial 0/0/0 interface on R2 is connected to the DTE end of the cable. The cable should be labeled either DTE or DCE. You can also distinguish DTE from DCE by looking at the connector between the two cables. The DTE cable has a male connector, whereas the DCE cable has a female connector. If a cable is connected between the two routers, you can use the show controllers command to determine which end of the cable is attached to that interface. In the command output, notice that R1 has the DCE cable attached to its serial 00th interface and that no clock rate is set. Once the cable is attached, the clock can now be set with the clock rate command. The available clock rates, in bits per second, are 1200, 2400, 9600, 19200, 38400, 56000, 64,000, 72,000, 125,000, 148,000, 500,000, 800,000, 1 million, 1,300,000, 2 million, and 4 million. Some bit rates might not be available on certain serial interfaces. Because serial 0/0/0 interface on R1 has the DCE cable attached, we will configure that interface with a clock rate. Note: if a router's interface with a DTE cable is configured with a clock rate command, the iOS will disregard the command and there will be no ill effects. As you can see from the figure, we can determine that the line protocol is now up and verify this on both ends of the serial link by using the show interfaces and show IP interface brief commands. Remember, the serial interface will be up only if both ends of the link are configured correctly. In our lab environment, we have configured the clock rate on the end with the DCE cable. We can further verify that the link is up by pinging the remote interface. Finally, we can see the 172.16.2.0/24 serial network in the routing tables of both routers. If we issue the show IP route command on R1, we will see the directly connected route for the 172.16.2.0/24 network. Now take a look at router R1's routing configuration by using the show running config command. Note: although the clock rate command is 2 words, the iOS spells clock rate as a single word in the running configuration and startup configuration files.